Good afternoon, everyone. Welcome to this webinar about valuable materials from sewage water. My name is Jappe de Best. I'm working at Avans University of Applied Science, the Center for Expertise Biobased Economy, and I will be representing the project today. It's good to see that so many people have applied for this seminar and that you are very much interested in valorizing sewage water. And today we will tell some of our results from valorizing sewage water in the WOW project, which is an EU and WE finance project. I have to mention at the beginning that maybe some parts of the presentations may have a high technical level, but if you have any questions, you can ask them in the chat and we will try to answer them as much as possible after the presentations, or possibly later by email if we do not have enough time to answer all your questions. And as a kickoff of this webinar, I first would like to give a brief introduction of the project WOW if you do not know the project yet. So I'm not sure if my presentation is visible yet, Jurgen. Yeah, okay, perfect. So I will first tell you a bit about the whole project of WOW, and then later on in this webinar we have 3 presentations who will go a bit deeper into the topic. Okay, well, as you all know, Europe's State of the Environment in 2020, I have this piece of information. So we need a change of direction urgently to face all the climate changes and challenges that we have and to prevent reverse degradation and ensure future prosperity. But fortunately, there's also always a nice view at the horizon. There is reason for hope, which I highlighted. There are lots of technological innovations going on, which are also supported by the European Green Deal, which was just started. And hopefully we, with the project WOW, can also contribute partly to this. Well, already when you look at sewage, there are many different researches going on in trying to make sewage into a valuable source. Well, the most commonly known is, of course, energy. So we can turn sewage into biomethane. But recently also a lot of different researches have been going on about producing resources from sewage. Some examples I put here, you have, for instance, Carmera, which is a soil improver and a polymer additive. You can produce humic acids from sewage. You can produce phosphorus, for instance, in the form of struvite. Cellulose gives an example here of some furniture made from cellulose. And finally, PHA bioplastics, which is also part of the project WOW. And of course, you also can look at clean water, fatty acids, metals, and organic matter. Unfortunately, up to now, sewage is not fully utilized yet. I guess at this moment, it's about less than 1% of the raw materials from sewage is reused. And there are many different reasons for that. First of all, I guess the potential is unknown by the markets. Secondly, it's also definitely still a challenge to extract all the raw materials in sewage. And thirdly, what we often see is that sewage has an image of dirty and unsafe, whereas we would like to see it as an opportunity. And finally, something that also prevents us from reusing sewage to its full potential is the legal framework to commercialize raw materials, which is quite complex at the moment in the EU. So this is why we started the WOW project about 1.5 to 2 years ago. And when you look at the WOW goals, we want to aim to start a transition towards a circular approach in sewage treatment. And for this purpose, we focus on 3 different things. First of all, we want to show that it's technically possible to recover raw materials from sewage water. Secondly, we want to create a European framework for the steps that need to be followed from waste to raw material. So help out the legislation. And finally, we want to let market parties become acquainted with the potential of raw materials from sewage water. So it will get a boost. Well, when we look at the end products that we would like to have as well at the end, which is in 2022, the first thing we aim for is 5 value chains from our bioproducts from sewage, and I'll tell you a bit more about that in a few minutes. Secondly, we have 3 pilots for the production of 5 different types of raw material. Thirdly, a supporting tool to help water authorities in their choices to a circular approach, and I will tell you more about that decision support tool in the last presentation of this seminar. And finally, a European legal roadmap. To tell you a bit more about the 3 WOW pilots in an overview, the first one we look at is cellulose, and we try to turn cellulose, which is toilet paper in sewage water, into bio-oil, biochar, and acetic acid, and we do this via pyrolysis. The second one is PHA, and PHA is a bioplastic. We do it by microbial PHA accumulation, and the second presentation will go deeper into this topic. And finally, we have lipids, and from lipids we can produce biofuel from microbial lipid accumulation. Well, when we first look at cellulose, well, as I already said, cellulose in sewage finds its origin in flush toilet paper. And first of all, it can be extracted by using fine sieves. And then when you have extracted it by fine sieves, you can use pyrolysis for the cellulose to transform it into a positive valued product. And we have 3 different products we produce. First of all, we have bio-oil, which can be used as a fuel. Secondly, we have biochar, which is an absorbent which can, for instance, be used for the removal of pharmaceutical residues. And thirdly, we have acetic acid, and this can again be used as a carbon source for sewage treatment. On the right side, you see a schematic of the process, but I will not go deeper into this in relation of time. Then secondly, we have PHA, which is a type of bioplastic. It's the abbreviation of polyhydroxyalkanoates, which is a fully biodegradable plastic. It's actually the fastest degrading bioplastic you can find. And what is nice to know is that bacteria that are present in the secondary sludge of a sewage treatment plant can produce PHA. And for this, they use the volatile fatty acids, which are already present in sewage. And what we do in WOW is we try to create proper conditions to enhance this PHA production. So to have more PHA produced. And in this way, we can use the VFAs, which are present in sewage, to transform it into positive valued products, which is PHA. So the bottom part shows you a bit how the process works. So we have secondary sludge on the left side. Then we have an enrichment on the substrate. So we favor the bacteria that can accumulate PHA. Then finally, we accumulate the PHA using the VFAs from sewage. And in the last step, we extract or we separate the PHA-rich bacteria from the other bacteria. And then, of course, you need an extraction or purification process, which is shown on the right side of this schematic. And finally, I would like to tell you a bit about lipids. So when you have bulking and foaming, which is a common problem in municipal sewage treatment plants, this is caused often by Microthrix parcivella, which is known to be responsible for this foaming and bulking. But what you can do, you can also use this Microthrix to accumulate long chain fatty acids, which are also present in sewage water or in sewage as lipids. And these lipids can next be harvested for biodiesel production. So in this case, we use the long chain fatty acids in sewage to transform them into a positive valued product, which is bio-oil. So this gives a brief overview of the different aspects of the different pilots we look into with WOW. And today we're going to tell you some of our first results in the project. We have 3 presentations. First of all, we will talk a bit about residual streams from sewage treatment plants as a source for PHA, bioplastic, and end products. Secondly, we will tell you more about techno-economic assessment of making bioplastics from sewage. And finally, I will tell you a bit more about a decision support tool for water authorities that can help you determine whether you can use your sewage in a circular manner. Well, this ends my first presentations. I would like to ask if there are any questions about this first part before we turn into the second presentation.
So far, no questions.
So far, no questions. Okay. It can be either be a good thing. So then I'll continue. So I'll introduce our next speaker, which is Guillaume Le Bouteiller. He's the technical and collaborative projects manager at Natureplast, and he will tell you more about the production and end use of PHA bioplastic. So the word is to you, Guillaume.
Yeah, I hope everyone is read me well. We try to share my my screen now. Do you see me or not? It's maybe not a good one.
Yes, we see you.
Yes. Do you see my presentation? It's okay?
Yes, we see it now.
Okay, thank you very much. Thank you, Yap, for the introduction. My name is Guillaume Le Bouteiller. I'm the technical manager of Natureplast company. We are a French company located in Normandy, and we are working for 13 years now on bioplastics materials, and we are specialized in bioplastics research and development and compounding. So today we make a short presentation regarding the way to produce PHA bioplastics from sewage, and this is what we are exploring within this very interesting project. First of all, I will present what are bioplastics and what are PHA. So bioplastics is a whole family of polymers that can be bio-based and or biodegradable. PHA are one of the material of the bioplastics family. And PHA stands for polyhydroxyalkanoate. So it's a polyester which can be obtained from two main monomers called 3HB for free hydroxybutyrate and 3HV for free hydroxyvalerate. And one of the main products into the market right now is a copolymer of it called PHBV. And the proportion of each monomer will determine the composition, the properties of the material. It can be soft to rigid, it can be very elastic, it can be very resistant to temperature. So this is a very interesting bioplastics, especially because it is fully bio-based, so fully obtained from renewable resources, and biodegradable in almost every conditions. This is one of the only biodegradable polymer which is fully biodegradable in water, for example, and this is very important for some of the applications we are currently developing. So currently, PHA are mainly produced from, let's say, standard biomass, such as cornstarch or sugars, obtained from sugarcane or sugar beet. So the standard PHA production process is using volatile fatty acids, so VFA, such as acid acetic or propionic acid, coming from sugars or starch, and which are transformed into a mixed microbial culture, MMC, through a microbial fermentation process from which you obtain a mix of PHA and residual bacteria. So then you have to extract the PHA and then to purify it. What we are trying to do in the raw project, as already said Yap in his previous presentation, is to use sewage and to use, for instance, primary sludge, from which we can obtain VFAs through acidification. And then we can obtain bacteria from activated sludge in order to do biomass enrichment, and then to do biomass PHA accumulation in order to get PHA enriched biomass. So within the WOW project, we have a PHA pilot team with the Kaiserslautern University and Wuppertal in Germany. We are working on pilot scale bacterial PHA production. Then the extraction and lab scale fermentation is performed by Avance. After obtaining the PHA Naturplast, so our company is doing extrusion, injection, and characterization of the material in order to then get the products. And Vito, the last part, we are performing the techno-economic analysis that you will see in the next presentation. So some examples of the pilot that it is currently under development within this project. So the first step in Kaiserslautern University is a pilot scale PHA accumulation, when you can see the acidification reactors using primary sludge, which are then pressed and in order to get the VFAs. The VFAs are then enriched, and then the fermentation process occurs, and you can accumulate PHA, which are then pressed and dried. Then you get a PHA enriched biomass. All these steps are contained in this container, okay, and all the equipment are in it. Then you have the extraction and purification, as already shown, of the biomass, which is from which we extract the PHA with a solvent called dimethyl carbonate. You recover the solvent and then you get the PHA. The PHA is then purified with butanol. Once again, you recover the solvent and then you get purified PHA. Here you can have a look of the kind of equipment that can be used for the pilot scale extraction. And what is very important and interesting in this process is the use of non-harmful and reusable solvent called dimethyl carbonate. After this stage, once we get PHA, this is where we are coming. And we use PHA through an extrusion process with 21mm twin screw extruders, which is standard equipment in plastic industry, in order to get PHA compounds with improved properties, because PHA you obtain after the fermentation, extraction, and purification is often very sensitive, very sensitive to thermal exposure and so on, and it has to be compounded in order to improve its shelf life, in order to improve its processability and the properties in use. So here we obtain a compound, so it's a mix of PHA with additives, other biopolyesters, depending on what we want to obtain at the end, which are then injected in injection machine, which is also standard plastic equipment, in order to get PHA products that you can see on this picture. So what can we do with PHA? And this is where we want to go at the end of the project. So PHA may be used in a wide range of applications, coming from food packaging or coffee capsules. Here you have some examples, if you see my screen. One application which is very important for PHA is water denitrification, because, as I said, this is one of the only biodegradable polymer in water, and it's used in aquarium or in aquaculture in order to help the bacteria to remove nitrogen from the water, because the bacteria comes and eat the PHA, and they are here to consume as well as nitrogen in the water. So here we have some examples, some small balls, injected balls that can be used for this purpose. You can also make vineyard clips. You can also make cosmetic packaging. It's a very interesting material because one of the functionality that will be used here is its ability to biodegrade really fast compared to most of the other biodegradable bioplastics. And it's widely used, it's more and more used for application where you are looking for degradation of the product after its use. So in order to conclude this presentation, where are we now with this pilot? So the pilot is close to finalization because operation will start next month, so in November 2020. After, we will be able to get the first kilograms of PHA, of raw PHA, which will be evaluated, so through extrusion, injection, and properties characterization, so in early 2021, and then will be compounded, as explained, in order to adapt to the market needs in 2021 as well. This is where I end my presentation. So thank you very much for your attention. We have created a small video, a small film about all the free pilot installations. So let's have a look at it, and in order to discover these free pilots.
Did you know that even used toilet paper can get a second life? Like this bench I'm sitting on. Recently, the European Commission launched a new circular action plan to make Europe cleaner and more competitive. And although encouraging progress has been made, there's still a lot of work to be done to reduce our emissions and to stop the ever-increasing amount of waste we are producing. Sewage is a largely untapped and endless resource for the circular economy. In the WOW project, we embrace the circular use of raw materials from sewage. Our aim is to motivate sewage treatment plant operators and markets for bio-based products to get to meet each other. We are doing this by starting up 3 different pilot projects. One to recover and pyrolyze cellulose, one for lipids production, and one for making PHA bioplastics. We are currently at the sewage treatment plants in Ede, where our cellulose pilot is under construction.
In North-West Europe, each person flushes away about 13 kilograms toilet paper per year. With the fine sieves, we remove this toilet paper with cellulose in it. We dewater, we dry, and we press it into pellets. After that, we pyrolyze it. During this process, products as bio-oil and biochar are formed. And the biochar can be used to remove micropollutants from sewage.
Lipids are often seen as a problem in sewage treatment plants. In combination with certain bacteria, they can cause bulking and foaming. However, accumulating lipids can also be a great ingredient for biodiesel. Our project partner from Luxembourg calculated that lipids from sewage can cover a significant amount for the biodiesel market in North-West Europe.
Apart from the cellulose and the lipids pilot, we also have the PHA bioplastic pilot. In this pilot, we work here in Breda along with our partners in Germany for the production and extraction of PHA bioplastic out of sludge or sewage water, and it works more or less like the human body. We aim to give bacteria volatile fatty acids, which is more or less like unhealthy food, and just like in us it makes us fat, for the bacteria it gives us PHA. After we make them fat, or we make them accumulate this PHA intracellularly, we extract this PHA out of their cells, and then we can test for applications. With the extract, we can then produce bioplastics like this one. Because they are fully biodegradable, they have the potential to substitute single-use plastics. And actually, PHA produced from sludge can already substitute 16% of all the PHA already produced worldwide.
In our project, we show you the potential of raw materials from sewage. More companies start to get interested, and we hope so are you.
Thank you very much for the film. Is there any question regarding PHA production from sewage?
No, I don't see any questions yet.
Okay, thank you very much. So now, please welcome Mohamed Nazir Khan from Vito company, who will present a Techno-Economic Assessment of making bioplastics from sewage. I leave you the floor, Mohamed. Thank you.
Thanks, Kilome. I have a pre-recorded presentation, so I would like Jürgen to play it. Good afternoon, everyone. My name is Mohamed Nazir Khan. I'm working as a researcher in Techno-Economic Assessments at Vito. Today, my talk is on the Techno-Economic Assessment of creating bioplastics from sewage. Let me start by giving a brief overview of our techno-economic approach. We start by market study, followed by creating a detailed process flow diagram of the value chain. Then we develop mass and energy balances based on the value chain, followed by economic assessment. The economic assessment is a dynamic process in which we identify the key important parameters that affect the final production cost. After identifying those parameters, we do uncertainty analysis to quantify the effect of those parameters on the final production cost. The advantage of following our approach is that it will reduce the time to take the product to the market. It will also help in devising the optimum strategies to use the available resources, and it also helps in identifying the areas where improvements can be done and thus setting R&D targets for the future. And it also helps in taking go, no-go decisions for the business case and also making well-informed decisions for the business model. This is the process flow diagram of producing bioplastics from sewage. The bioplastics considered in this study are called polyhydroxyalkanoates, in short PHAs. In the diagram, you can see that the red bordered boxes are the connections to the classical wastewater treatment plant, and the shaded boxes are optional steps which may or may not be required in this process. The process starts by taking a primary sludge and supplying it to the fermentation reactors, which are 7 in number in this study. And this is proportional to the sludge retention time, which is 7 days, just to make the process steady. After 7 days, the volatile fatty acids are produced, which are separated out in a separation step. The solids from this step goes to the digester of the wastewater treatment plant. The volatile fatty acids are split into 2 streams. The first stream goes into the enrichment reactor, where the biobased bacteria mix from the waste activated sludge is also supplied. Here, the bacteria which produces PHA are enriched, whereas the other bacteria are killed off. The biomass from this reactor goes into the accumulation reactor, where the second stream of volatile fatty acids is also supplied. Here the bacteria feed off on volatile fatty acids and produce PHA. Here you can also see that we are also supplying acetic acid, which is an optional step in this process. The output from the accumulation reactor goes to a separation step where effluent is removed and sent to the wastewater treatment plant, and the PHA-rich biomass is dried out in a dryer, followed by extraction step. In the extraction step, we use a solvent called dimethyl carbonate to disrupt the cell walls of the bacteria. The solvent is recovered in evaporation, and in this step we also get raw PHA. And the raw PHA is mixed with some other raw material like biopolymers in certain plastic processing technology, like injection molding in this case, to get the end product. So in the later slides, I will present the two different set of results. So one set of result is for the PHA itself, and the other set of results are for the end product. These are the economic results for the PHA production. As you can see that the top product shows the capex and opex breakdown. In the capex breakdown, the major contribution comes from the enrichment and accumulation reactors, about 60%. In the OPEX breakdown, we can see that the major contribution comes from the labor, which is a fixed cost, followed by heat required in drying process. In the figure on the bottom shows the minimum cell production cost of the PHA. We estimated about 2.74 euros per kilogram, which is significantly lower than that reported in the literature. You can see that the major contribution comes from the fixed cost, followed by the heat required in the dryer. Here also you can see that the share of acetic acid is also quite significant. So if we avoid using acetic acid during the enrichment and accumulation stage, then the cost can be reduced further. These are the economic results for the whole plant, including the plastic processing step. Here we have assumed that the blend ratio is 70% PHA and the rest is some other biopolymer like polylactic acid. Here, when compared to the PHA production plant, we see that there is an increase of 20% in capex and increase of 67% in opex. The increase in opex mainly comes by using the raw material along with PHA. In the next slides, I will present the results of Techno-Economic Assessment as a function of key parameters which we have identified in this study. The key parameters identified are the plant scale, the PHA yield in accumulation reactor, cell disruption efficiency in extraction step, certain economic external factors like the prices of natural gas, acetic acid, raw material, and for the end product, the blending ratio. The results here shown are for the PHA production cost and also the end product production cost as a function of plant scale. The plant scale is shown in terms of ton of sludge per day on the x-axis. The base case assumptions are given below. The base case value for the plant scale is 650 ton of sludge per day. As you can see that if we go from 300 to 1500 ton of sludge per day, the cost of production for PHA and for the end product decreases significantly. The reduction is for about 42% in the PHA case, whereas it is 34% in the end product case. These are the results with respect to PHA yield in accumulation reactor. The base case value assumed is 35%. So if we go from 30% to and manage to go up till 70%, there is a significant reduction in the PHA production cost. It is about 57%, whereas in the case of end product, the reduction is about 39%. These are the results with respect to cell disruption efficiency in extraction step. The base value assumed is 100%. However, in real practice, it may be lower than 100%. Since we see that the effect is not that significant, so we can manage having efficiencies lower than 100% here. These are the results for the PHA production cost with respect to the natural gas price and acetic acid price. The natural gas is used in a drying step. Therefore, if the natural gas price is reduced, the PHA production cost also reduces significantly. In other words, we can also say that if an alternative drying process is identified, which consumes low energy, then the PHA production cost can be reduced significantly. Similarly, for the acetic acid, since this is an optional step, if we can avoid using acetic acid, the PHA production cost can be reduced further. These are the results of the end product price with respect to blending ratio. For the base case, the blending ratio was 70% PHA and 30% raw material. However, if we increase the percentage of raw material in the blend up to 80%, we can see that the major contribution comes from the cost of raw material itself. From the figure on the right, we can say that if the cheaper raw material is used, the end product price can be reduced significantly. From these assessments, we have estimated that the PHA can be produced at a price range of 2 to 3 euros per kilogram, which is significantly lower than that reported in the literature. We have also identified the key parameters that affect the production cost, like plant scale and PHA yield. The external economic factors like the natural gas price and acetic acid price are also significant. And for the end product, the blending ratio and also the cost of raw materials are significant. We have also identified certain areas where further research is required, like the sequential batch reactors used in enrichment and accumulation steps. We have seen that the capex contribution from these two reactors is quite significant. It was about 60% of the overall capex. So if there is an alternate reactor configuration that can perform the similar operations with low capex, then the cost of production can be reduced to a certain extent. We have also seen that the heat required during drying process is also quite significant. So if there is any alternate drying process with low energy consumption, the cost of production can go significantly down. And the PHA yield in accumulation stage is also a quite key parameter. If it can be increased from the base value of 35%, then the production cost can be reduced quite significantly. The disruption efficiency should be maintained as high as possible by using cheaper solvents, and it is a critical area to be looked into. And the most important thing is to develop efficient instrumentation control strategy for operating these type of plant. And finally, if cheaper alternative raw material can be identified, which can be combined with PHA to produce quality product, then that would also reduce the cost of the end product significantly. These are the partners involved in WOW project. We would like to acknowledge Technical University of Kaiserslautern for providing the technical data for the PHA plant. On the right is a wonderful team at Vito working on techno-economic assessments in WOW project. So that's it from me. If you have any questions, I would be happy to answer them. Thank you.
I don't see any questions now.
Okay. So in that case, I would like to give the stage to Yapa, who's from Avans University, and he will talk about the tool for water boards and how they can use sewage water in a circular manner. Yapa.
Always good to unmute. So what I said is it's the final presentation of today will be from me. As I told you before, I will tell you a bit more about the decision support tool that we are currently developing, and I'll share my screen. So hopefully it's visible right now. Okay, perfect. So about the decision support tool, which is one of the products we are developing within the WOW project. What I will tell you in the next 10 minutes is, first of all, a bit about the goal of the decision support tool. Next, I will tell you what the decision support tool is about and what the results of the decision support tool show you. And then, of course, what I would like to do is I would like you to show you the decision support tool so you can actually see what it looks like and how it works. And then in the end, we still have some time left for questions. So first of all, the goal of the decision support tool is we would like to support and stimulate water authorities to realize their sustainability goals. And in order for water authorities to decide to do a certain investment on a certain technique, of course, you need to know whether the techniques that, for instance, we have developed in the WOW project are feasible to do at a certain sewage treatment plant. And besides helping water authorities in making their decisions, we also want to show policymakers the opportunities for the recovery and reuse of, in this case, carbon-based elements from wastewater, because that's what WOW is focusing on. Well, what is the DST? The DST is an Excel tool, which I'll show you in a few minutes, for water authorities that operate sewage treatment plants. The DST can be used to get a first impression if the influent of a sewage treatment plant is suitable for the recovery and reuse of carbon-based elements. So it only gives a first impression. The DST looks at the 3 different activities that WOW is focusing on. So on recovery of cellulose, on PHA bioplastic, and on lipid production. And what is also important is we try to use a limited amount of input parameters, which usually are readily available for sewage treatment plant owners. So you don't have to get a lot of data to be able to use the decision support tool. And based on the outcome of the DST, you can decide if the technology for either cellulose, PHA, or lipids is worth a closer look. As I already said, it gives you a first impression, and if it gives a positive outcome, you could have a further study to see if it is a really feasible technique. Well, when you look at the outcome, we have 3 different outcomes. So it says the composition of an input stream, so the information you put in of a sewage treatment plant, can either indicate that implementation of the technique for cellulose, PHA, and/or lipids is very promising. So that would mean you would like to take a further look to see if it's economically feasible and if you have enough square meters available to put the installation and stuff like that. The second one is, of course, obviously that the implementation of either of these techniques is not feasible. So it's not worth taking a further look. And the final one is that it's not clear yet if the implementation is feasible and a more detailed consideration is needed. And this is when you put in numbers which are close to the ranges that we have used within the decision support tool. So it means you have to take a closer look. Well, when we look at the results of the DST, it provides you information, well, first of all, of the effects of the WOW technologies on other sewage treatment plant processes. I can imagine that some sewage treatment plants already produce biogas, for instance, or you already have struvite recovery, phosphorus recovery. Then you would like to know if you implement, for instance, PHA production, if it would affect one of these processes. Well, the DST gives you more information on that. Secondly, it gives you information about the technical aspects, which is based on the pilots that are currently running within the project. Also information about the economic aspects, and this information comes from the Techno-Economic Assessment, which Mohammed just told you more about. Thirdly, it gives you, or fourthly, it gives you information about the environmental and sustainability aspects, based also on the information from the pilots. So does it have an effect on the environment? Is it positive, for instance, for the carbon footprint? So that kind of information. And finally, it gives you information about social aspects. So is it, for instance, giving a lot of smell or a lot of noise, visual pollution? So that's also mentioned within the DST. Well, what does it look like? So now I would like to take you to the concept DST, what it looks like. So I will end this presentation and share with you my screen with the DST. So if I'm not mistaken, by now you can see the decision support tool, which is an Excel tool, as I already explained to you, which consists of 5 different tabs. The first one, which I showed to you here, is the manual of the DST. It gives an overview of what the DST does and also how it works. So here on the bottom, you can see what you need to do to be able to work the DST. As you can see, there's not much instruction, so it is quite simple to use. And for the working, I would like to go to the second tab of the decision support tool. This is what it looks like. So this is the input tab. And here you have to put in some basic information. So here on the left side, you see the information that you need to put in. Well, the name and the location. For now, I put in sewage treatment plant Aquarama and the online as the influent stream. And then you have a couple of questions. So first question would be, is there a primary treatment at the sewage treatment plant? Well, I will fill in some information here. And what you see also with the red triangles, if you go to the square, it will give you more information of what to put in. And what you see is, because I filled in no at this case, you already see a change in color. So when you have no primary treatment, it would mean that producing PHA bioplastics is not feasible anymore. Well, the other questions that you need to fill in is the percentage of sewage water from households, the amount of population equivalence, the BOD-COD ratio, and finally the COD. So for now, I'm going to put in some numbers to show you what happens randomly. Finally, COD, I will take 300. So here you will see that the different colors change within the decision support tool. So for each of the parameters that you need to fill in for each of the three recoveries that we look at in WOW, it will give you an outcome, and it will give you in the color, and the colors are explained over here, which match the ones that I also showed in the presentation. It will tell you whether it's feasible, yes or no. And if you want to know why it is feasible, yes or no, again, when you go to the triangle, it gives you an explanation which ranges we have chosen for a positive or a negative outcome of the decision support tool. So then you have the final results. And of course, I've chosen numbers to see the three different ones. So green, in this case, the cellulose recovery would be feasible with this input stream. The biodiesel would not be feasible. And for PHA, more information is needed. So this is the first outcome, and then we have three tabs left. So for each of the different techniques, we have a fact sheet, which gives you more information about the technology. So I'll briefly explain this to you. So first of all, on the left top corner, you see the possibilities of implementation. So it gives you the information on the top we see previously, but now it gives you also an explanation of the color. So that gives you a bit more information. Here on the right top side, what you can see is what I already told you, the possible effects on other processes at sewage treatment plants. So you could have an aerobic secondary treatment, you could have an Anamox or a Nereda. It could have an effect on coagulation or flocculation of your sludge. And here you also see other processes, so for energy, nutrient recovery, or other recovery processes. And you have three different options. So the pink one says it has no impact on the process. So in this case, PHA production has no impact on struvite recovery. The yellow one, it does have an effect, possibly has an effect, I'm sorry. And the brown one says it does have an effect. And again, when you go to the triangle, it gives you more information about the specifics of the effect. So if it's positive or negative. And of course, you can take that into consideration. And then finally, you also have the fact sheet, which gives you more information about the technical aspects of, in this case, PHA production. So the dimensions of the pilot, the status of the technique, electricity use, and other parameters. It gives you information about environmental and sustainability aspects. As I already told you, odor, noise, visual aspects. You have the economic aspects. So CAPEX, OPEX, main influencing parameters, and you have the social aspects, so health and safety, acceptability, and legal aspects. And as you can see, not all information is filled in yet because the pilots currently are still running, but I will show you one for cellulose, which for instance already has the economic aspects filled in. So we hope to fill in all this data during our project and in the end have a complete filled fact sheet for all of the different techniques that we use. Let me see. Well, that ends for me the presentation about the DST. I'll quickly go back to my presentation to see if I have any left out, because no, the next slide would be if there's any questions or questions left about the DST. So if there are any, yeah, please ask them.
Yes, there is a question. Is biodegradable plastic safe enough to use in the food industry or food packaging, for example?
Good question. That is something we, and that also has a relation with the legal aspects that we are currently looking into. So that is something that still needs to be tested, whether it could be applied, but currently not, because indeed you have certain regulations about food applications of plastics which are made from a residual material. So that's something we are still looking into, but I guess in the end it could be an option.
Okay, thank you. And another question, what are the changes in PHA as it degrades in soil and water?
The effect of the degradation of the PHA, you mean?
No, the PHA.
Yeah, so the PHA when it ends up in the environment in the end. Is that the question? Because I'm not... Yeah, the effect on the pH, I guess when the degradation, I don't know, but I don't think so. The degradation of PHA has an effect on the pH of soil or water, because it is made from VFAs, but I'm not sure if it also degrades into VFAs, because the degradation will be done by bacteria and they will consume the PHA, so they will use it as a carbon source. So I don't think it does have an effect on the pH.
Okay, thank you. And when is the final version of the DST available?
The final version will be available in the second half of 2021, because as I just explained, we want to put in all the data that we get from the pilots, and we think the pilots should be finished somewhere in summertime 2021. So then after that we can finish the DST.
And is it freely available for everybody?
That's the idea, yeah. So as soon as the DST is finished, it will be published on the WOW website and of the websites of the partners within WOW.
Okay, and how specific are the outcomes of the DST?
Well, good question. That depends a bit on the outcome of the pilots. So the more detailed information we get from the pilots, the more detailed we can be in the DST. So that's difficult to forecast at this moment. So it would mean that if we have less detailed information, that the ranges will be a bit bigger, so you have more options to the outcome that we do not know yet whether it's feasible, yes or no, if that makes sense.
Yeah, thanks a lot. That were all the questions. Okay,
then thank you very much for the questions, and I would like to thank everyone for participating in this webinar. I hope you got a lot of useful information about the things we are working on in WOW. And of course, if you are interested to know more about WOW or to get involved in the project, you're very welcome to visit our website of WOW, and there you also have the contact information. And finally, what I would like to say is that we will share the presentations with you. So if you want to look something up, you can always find them in the presentations. So thank you very much. And well, hopefully we see each other live at some point later on. Thanks.